Our speaker today is Dr. Alan Jeary. He's the Chief Technology Officer and partner of STRAM Group, which is a company that provides structural technology analysis. Dr. Jeary has more than 35 years of experience in his field. He holds 2 doctorates and has published more than 300 papers. Among his long list of accolades is serving as consultant for the largest structural engineering firms in the world and receiving the Telford Gold Medal from the Institute of Civil Engineers in the United Kingdom. During the last year, Dr. Jeary and his company were awarded a Professional Excellence Award by the Australian Institute of Building for work on the subject of his talk today, which is titled Recent Experience with Decoding Information from the Performance of Structures. If you have questions during the talk, please type them into the chat room and Dr. Jeary will address them at the end of his talk. So welcome, Dr. Jeary, and all participants, and thank you for joining us today.
Thank you very much. And ladies and gentlemen, it's a pleasure to be able to talk to you today and to share with you some of the things that we've discovered as a company and I've discovered as a person as we've gone about our business. So let's get straight into it. Okay, the first thing that I want to start off with is by saying to you that we've had a lot of experience over the last 10 years of monitoring structures and looking at their integrity. And we've been doing that for the purposes of commercial investigations. Before that, I was previously a chair professor in universities in various places in the world and looked at these things for research purposes. Before that even, I was involved in research with the British government and with the Electricity Authority in the United Kingdom. So there's a wealth of experience and I'm wanting to share with you the majority of that. So the reasons for looking at things, both from the research purpose and for the commercial purpose, is when there are doubts about the continuing integrity of the structure. And we have 2 different possibilities. One is a visual inspection of the structure, and the other is actually making measurements of the performance. So in practice, what we do is to make those measurements because there are severe advantages. There are also other reasons that we might take a look, and perhaps the biggest of those is a change in the perceived risk. Now, the perceived risk may change as a result of visible damage to a structure, codes of practice changing, and new design considerations, or there may be changes to the Earth's climate, for instance. So what this presentation is going to be about is particularly assessing a structure, especially after an event which has taken it into a large amplitude range, and assessing the ongoing need for maintenance as well, with an implication for life expectancy of the structure. I'll come back to that. But the biggest thing about this is that it's cheap, it's quick, and it's relatively straightforward. I think I'll present in this mode. The whole idea is that we can look very quickly at structures on either side of an event. Now, this is when there is a low amplitude of response. So the diagram here of an acceleration time history of a real structure is we have something before the event, we have the large amplitude event, and then we have a low amplitude event after the event. If there are changes to the structure, then they are apparent both before and after. And you can, at your leisure, compare the before and after. Traditionally, people involved with high amplitude events, such as seismic engineers, will take the information that they can from that high amplitude event. But if there are changes to the structure, and I'm going to show you why, those changes will be apparent in the low amplitude response as well. But better than this, you can actually take your time to take a look at what's going on. Let's look at the background risk, first of all, and particularly I want to look at bridges. The infrastructure report card said that we have a very large number of bridges in the United States that are not up to scratch, something like 10% of the infrastructure there. If we break it down a little bit further, then we look at the age of the structure, and clearly with 40% of them, they are older structures. And if we look at the deficient bridges, then we see that it's getting better, but nevertheless, the number of deficient structures and the number of deficient structures by area is still unacceptably high. So what do we do about it? Well, first of all, let's take a step backwards and look at not the performance of the structures, but how we got to this state. And the first thing is to say that probably the biggest event in the design of bridges was the Tay Bridge disaster in 1879, in which the design originally had taken 10 pounds per square foot as the loading. And on a day which had a nasty storm, then there was a speeding train going north, and there was a wind gust, probably only about 65 miles per hour, and the bridge collapsed. The train fell into the river, and a lot of people were killed. Now, what happened there was actually that the designer, who had the ultimate responsibility, was actually the Astronomer Royal in those days, and he was pilloried. He was described as somebody who didn't know what he was doing, and was fired from his job, died a pauper. But look at those figures. It was a 65 mile per hour gust. We wouldn't dream of designing for a 65 mile per hour gust these days. In fact, we design, generally speaking, these days for at least 110 miles per hour. And when you consider that the force is a squared function, then you can see that something is wrong there. Well, recent research has actually looked at some of the remains of that bridge and found that fatigue damage was probably a problem. And in fact, maintenance crew recorded back in 1879 that they could hear parts of the structure chattering. In other words, the connections weren't good ones. And of course, we don't do that anymore. Well, I have news for you. I'm going to show you an example of where we still are doing that kind of thing. So we learned from that Tay Bridge disaster. We learned from the San Francisco earthquake and the Tacoma Narrows Bridge disaster. And we then, in the 1950s, started using prescriptive requirements for design. 1989, we got to goals, and that was in which we were beginning to look at the performance of structures. We first started looking at the risk of occurrence of a collapse or damage to a structure. And that's the way that codes have been going until very recently. What they do is they try to assess the risk of an occurrence of something, a wind or an earthquake. For wind, it's easier. There are more often, they happen more often, but nevertheless, we are designing, and we talk about the design for a once in 50-year wind in the United States. In other places, we talk about a probability of 0.02. And if we've got a structure that we really don't want to be damaged, we take a probability of even less than that, or a return period of far greater than that. 4,000 years we use typically in Australia for buildings which are something that we really must rely on after an event. The problem with calling it a once in 50-year event is that popularly people get used to saying, it's only been up for 1 year, so it's still got 49 years to go. Well, that simply isn't true. It's a probability of 0.02 occurrence every year. So we give a false impression by talking about that return period. So from the Tay Bridge through to 1989, the codes went from 15 pounds per square foot. They went up to 30 pounds per square foot after the San Francisco earthquake. We used a quasi-static approach, and we allowed people to follow a code which told them what they had to do. Fire codes were the first that looked at performance. So instead of saying you had to have a door which was 2 inches thick, you said you can build it any way you like, but it must last at least a certain amount of time with a certain intensity of fire. Well, since that time, in a small way, we've been doing that for earthquakes and for wind. And what we're doing is saying, well, there are people who use these structures and they must be comfortable. The structure must not fall down in the event of a large event. There are some things which led us into the ability to be able to do this. The first was a paper by Brian Ellis, who took research data from around the world, including California, including the United States, Europe, Australia, New Zealand, and came up with the best fit for the frequency of fundamental frequency of a tall building of 46 upon H, where H is in meters. Just recently, ASC 716, which is a standard called by the codes of practice in the United States, calls it 150 upon H, where H is in feet. It's the same data, uses the same buildings as well. So it's not surprising that they come up like that. For me, I contributed to the understanding of nonlinear damping, and that was through a system of shaking buildings in the UK and Europe and looking at the response. We shook 40 buildings, dams, and chimneys, and have actually done more shaking tests than the whole of the rest of the world put together. One of the people who did one of those shaking tests was Ron Mays, who is now based in California, but he's the only one who's done a shaking test whereby he's gone past the elastic limit and into the nonlinear zone. So I would like just to talk about some of the things that have been happening recently and why we should be quite so interested in this. First of all, in 2018, we had the Ponte Morandi in Genoa, which collapsed. And it has been rebuilt in 22 months. And the replacement bridge, there's a picture of it, cost 216 million US dollars and took only 22 months to repair. There was a bridge collapse in Sao Paulo in Brazil, just by the side of the Rio Pinheiros. And if you look underneath the bridge, then what you find is that there are supports which have just collapsed under its self-weight. And if you look in the circled area there, you can see that the viaduct fell down about 2 meters because of the collapse of the supports underneath the structure. Talking of Tacoma Narrows, then there's been a second bridge over there. And of course, we know what the aerodynamic instabilities were, And so we can very much more easily design for wind forces on the bridges, knowing that they are going to be dynamically sensitive anyway. So the reasons for making measurements. Visual observation is very variable. People take checklists and put ticks against certain things that they've seen, but measurement can be precise, and the analysis can be about holistic behavior, the way that a structure is behaving holistically. In 1989, National Science Foundation and NIST produced a paper. It had 48 recommendations about what we should do for looking at the way that structures are behaving. And 30 years later, most have materialized, but some did not. And the key recommendations that are still not broadly applied are that finite elements should be calibrated. System identification and damage detection should incorporate non-linear analysis, and measurements for the assessment of performance should be done. We should share information between countries. Now, National Science Foundation and NIST had, at that time, the National Bureau of Standards. I was working at the time with the Building Research Establishment in the United Kingdom, and that's where we were doing the induced vibration tests. So we were already looking at performance, and that's perhaps why that recommendation is there, that sharing information between countries is a good idea as well. So now let's look at the physics of the structural assessment. First of all, we can use Newton's laws of motion, but we must recognize that they are an approximation. They're a good approximation, but they only approximate, and I'll tell you why in just a moment. They're satisfactory for engineering purposes. We need to know the mass of the structure, the position and elements and overall geometry of the elements. We need to know stiffnesses. We need to know input forces, the response, and the biggest one of all is damping. For so long, damping was just too difficult, so people swept it to one side. There is no need to sweep it to one side anymore. So the big thing about this is that we can look at the structural behavior of an entire structure. So instead of, as we do in college, working from individual element properties and then working up to what the entire structure is doing, we can look at the entire behavior of a structure and work down into the detail. And so we avoid the problem of the description of connections. So clearly we can work from basic equations, summing up the forces. We've got a familiar equation, mass times acceleration plus damping times velocity plus stiffness times displacement equals the imposed forces. There's a problem already inherent in there because damping is times velocity, and damping is simply not proportional to velocity. I'll tell you why in just a minute. So what we do is to say that we can solve that equation for generally, and we say that the response is a force times the stiffness upon, and then a complex function dependent on the frequency response. Let me just see if I can make this work here. What we say is that if we set the frequency to 0, then we have the static response. We get the displacement is the force divided by the stiffness. If we set the frequency to resonance and solve that equation, we get the displacement is the force divided by the stiffness and a dynamic magnification factor. So there we go, response equals force divided by stiffness, response equals force divided by stiffness, and the dynamic magnification factor. And there is a relationship between the static response and the dynamic response. And this is it. This is the complex frequency response function for a single degree of freedom system. And you'll see that when F equals Fn, then we've got a resonance. And that's the dynamic response. If we go back down to zero frequency, then what we've got is a 1 value there in the response and in phase response. That's the stuff that we do in college. As far as we're concerned, when we're dealing with dynamic structures, then we must look at the dynamic response as well. But look at that, it's a single diagram and it relates the static and the dynamic response. So if we measured the dynamic response, we've got a handle on what happens statically as well. Not necessarily easily, but it is there. Now, inside all this is that damping divides the different disciplines, and reconciliation is now available and possible. And that's because for the seismic engineers, they would tell the wind engineers, you just cannot measure damping at high amplitude. Wind engineers would say, there is so much information here, you really need to look at it. And there's a particular problem here in the interpretation, because at high amplitude, the damping parameter can vary more than 10 times the change in the frequency. Frequency changes when you get into the ductile behavior, but that does make a difficulty for measuring during earthquakes, because you've got a very small time for the analysis to be made. And that's why I started off with a diagram saying before, event, afterwards. If you take a measurement before, you've got a long time. For a random process, you need to get the random errors to a small enough amount that you can actually make intelligent choices about the interpretation of what you're seeing. So it's not difficult. It's certainly not impossible. And for long-term random excitation, it's easier to do at low amplitude. Now, if you are using low amplitude, then you could also use a breath of wind, people walking around, traffic. You do not have to wait for the large amplitude events. Additionally, if you reverse engineer damping, it contains a lot of information about the structure. So what I'm saying to you is, here is something new. It's only been available in the last 5 years, but if you measure for at low amplitude for a long time, then you can get a lot of information about the structure. When we enter the nonlinear zone, stresses redistribute. There's the possibility of looking at failure modes. But if we're designing, even nonlinear programs rely on linear approximations for at least part of the analysis. What we do then is put in some guesses. The design engineer needs to use his experience, his or her experience, and make assumptions about the way that a structure is going to behave. And they will then put those approximations directly in. The biggest one of these approximations is with damping, because it's a non-dimensional parameter and it's difficult to get an assessment of what it is. So by making measurements, you can actually look at the overall behavior of the structure, and you then have a direct relationship with modes of failure. Resonance we can use. The bigger or lighter a structure, the more likely it is to be excited dynamically. This is the Van der Hoeven spectrum, which was produced near to here, and it shows that there is a micrometeorological peak. This is measuring wind forces. There's a maximum about 1 cycle every 40 seconds. And then there's the spectral gap. And then we have a daily variation, night and day. We have a 4-day maximum as well. And then we have an annual maximum. Why do we have a 4-day maximum? because that's the average time that it takes for a weather system to go past a point on the Earth's surface. So until very recently, the best weather forecast statistically was same as yesterday. You'd be right for better than 50% of the time. Now, if we solve that equation or go back to that solution, then what we can say is that the displacement upon the force is 1 upon 8 zeta f squared m pi squared. What that is displacement, the force, which is dictated in the codes of practice, given that you're choosing a risk factor. There's a modal mass, mr, and then the zeta, which is the damping ratio, and f, which is the natural frequency. If you're a seismic engineer, you'll want to consider 1 upon f, which is the period of the structure. Same thing. But if we are taking the before and after event, then what we have is the modal mass is unchanging. It's the same structure. So if we measure the displacement per unit force, instead of displacement and assume that we have to measure a force, then what we have to do is take those 5 parameters into account. Whereas if we're making a measure before and after of displacement per unit force, we can eliminate the modal mass from the equation, and we can look at damping and frequency to give us all the information that we need. However, I did say that we have an approximation that we've made with Newton's second law of motion, and that is that frequency and damping are linear functions, but they're not. They're actually nonlinear. And to make this equation work, you need to analyze the nonlinear behavior. We know that there is a linear range because we all use Young's modulus. In college, we take stress strain curves, and throughout the elastic range, we've got a constant, which we call Young's modulus. At low amplitude, the soil structure interaction is small, so the response is governed by the structure. We must get past a number of nonlinearities which really don't give us any favors. But what we can do is convert at an amplitude, or take up to an amplitude which is within that linear range, and we can then compare before and after events. This was our vibrator system that we used in the BRE, Building Research Establishment, in the 1970s. And what we found was that if you turn that equation back and you create forces, different forces, you find that the frequency changes and the amplitude changes and the damping changes as well. But if you use that equation and instead you calculate what the mass is, then what you find is that the mass stays the same despite the fact that these parameters are varying in a nonlinear manner. So we know the equation works and that we can use it. All it says to us is you must measure that nonlinear response of frequency and damping. And it works all the time. This is, my apologies for the state of this, but this is real data from back in 1984. And this is a real response. Again, different building, but you can see that the modal mass of the building was pretty constant, despite the fact that in this particular case, damping changed by a large amount and frequency changed by a relatively smaller amount. But you see, the problem is that we're brought up like this. We are told in college that we do tests on individual elements, and we look at the forces and we try to sum those up when we work in the big wide world. But we spend little time working about how joints work. Far better then to look at the holistic behavior, and you work your way down into the individual interactions of various parts of a structure. So this is what we do. We measure the performance at an early a time as possible, which we call the baseline. We compare that performance with what's assumed in the design. Well, now we have the assumed frequency appearing in standards which are called up by the code. And we now have as well a mechanism for damping, which started off in the 1980s and was modified so that we could measure nonlinear damping. And as you can see with what I was showing you here, the damping is measurable at different amplitudes. In this particular case, we stopped the structure at different amplitudes, let the decay occur, and measured from the amplitude, from the envelope, exactly what the damping was at different amplitudes. So what we have is a way of predicting what damping is expected to be. We can do that knowing the frequency and knowing that the damping has a relationship with the frequency. It starts off low in a low amplitude plateau. It rises depending on the material which is participating in the vibration. And then when all mechanisms of damping, of energy dissipation are taken up, it reaches a high amplitude plateau. So we measure before and we measure after. And a baseline, we can compare with what the code requirements were and what the frequency and the damping are expected to be. Compare that and we get a risk ratio between what we've actually got and what the code required. If we measure after an event and we see changes in the structure, we can make a new comparison and we can compare that event, which will take the structure outside the elastic limit, and its return period as well. So everything is based on physics, math, system theory, and fracture mechanics. Now, fracture mechanics enters because we no longer say we've got hysteretic damping. What we've got is, inside a structure anyway, we have slip-stick mechanisms. And if you sum up an enormous number of them, you get a value which you could describe as equivalent viscous damping. Now, everybody assumes viscous damping. They've forgotten that it's equivalent viscous. But equivalent viscous allows us to make the calculations that we have to make. But now we've got the stick-slip mechanism for structural damping. We can actually predict and reverse engineer for damping to tell us what's really going on inside a structure. If we measure the response, we really have to use very good instrumentation. And we do, instrumentation that's so good that it can measure to better than the wavelength of visible light. This is what we do with the risk ratio. Use that equation and compare what we expected with what we should measure. And then we have the risk is the measured response over measured performance over the expected response. And that way we can convert that to a number of different things, not just a risk ratio, but a return period, the probability of occurrence every year, that kind of thing. And when we put the values that we've taken into a graph and look at the risk ratio, form a probability diagram, and there are a number of different things here. Median value for New Zealand buildings is about 112%. The value of 1 for a risk ratio means that it's met the minimum requirements of a code. We find that from our induced vibration tests in the UK and Europe, we had a median value of about 110%. In Japan, they have 120% because they have both typhoons and earthquakes to deal with, so they like to be sure. But everybody designs to about 110% as a minimum because we want to be safe. But look at the left-hand side here. there are outliers. And that probably mirrors what's going on in that report card, which says there's a lot of our infrastructure in the United States which is below what we consider to be acceptable. It's been going on for a long time. Now, these data come from 800 plus tall buildings. However, I want to turn our attention now to bridges, because we've got a number of different things that we can do. We have a structural cardiogram, which we take out to sites. We have triaxial accelerometers, which are capable of discerning motion to better than wavelength of visible light. The SKG can use solar power and can send data up to satellites if necessary. We prefer to have a direct connection with the internet, but it's possible. And we're interested in both capacity and risk. So if we're dealing with the nonlinear behavior, then we've got this linear area here, and we'll extrapolate up to a point where we can no longer use a linear relationship. After that, we've got to take ductility into account. But we also are interested in risk. I said to you, I don't like it being called a once in 50-year return or something like that. This diagram here was produced by my colleague, John Main, at the Building Research Establishment. What he did was to say, okay, supposing we have 5,000 years of history of windstorms, and let's put a red dot in here for every time that we get that once in 50-year event. Well, it's a random process. So what you find is that in each 50-year period, sometimes you get some, sometimes you don't. Sometimes you get 3 or 4, sometimes you get 0. What this actually says, and of course, there are 100 periods of 50 years in there, you find that only 63% of them, 63 of them, have the once in 50-year event. And that's because the chance of a 50-year event occurring in a 50-year period is 63%. So it's a random process, and that sums up why I really don't like calling it a once in 50-year wind. It's a probability 0.02. Can we do it for bridges? Well, the first thing that we need is to look at the frequency that occurs. And a number of people have looked at the expected frequency of long span bridges. This is a diagram in the bottom left here by Reto Cantini, who I worked with on Eurocodes for a while. And he showed that for bridges, that fundamental natural frequency is also predictable. So that's good. It also depends on the structural form. If you have a difference from a long span bridge, or you have a stone arch bridge, something like that, the damping will be different. Depends on the material used for construction, soil structure interaction at high amplitudes, and the materials as well. So is damping predictable? Well, stone arch structure values are precise. Cable stayed structures have higher values than experience with other structures would suggest. Cable hangers can introduce energy loss if connections are loose, and viaducts are also predictable. Here we have a measurement from a bridge that I'm going to show you some more detail of in just a moment if I have time. The three-part curve for damping, which says it starts at a low amplitude, which is correlated with the fundamental natural frequency, and then rises depending on the material, and rises until it gets to an amplitude where there's nothing else to dissipate energy. In this particular case, we've got high damping at low amplitudes, and we've got then dropping back to a value which is correlated with the natural frequency. This was about 0.19 hertz, period of about 5 seconds, and then a gradual rise. and the amplitude there is 3 times 10 to the minus 3 of a g. Now suppose that what's happening at low amplitude here is the interactions with the abutments, with the connections to other things, with aerodynamic influence on the structure as well. Then what we've got is that 3-part curve actually occurring. And what it means, no matter what we choose, a 5th order regression, these extra interactions occurring, or that 3-part damping curve, when we get up to an amplitude which is associated with the design, then all of them come together. And the value that we've got is something which is predictable. So our platform includes the hardware, software, and algorithms, not only to capture the data, but to analyze the nonlinear response. If we have a small enough structure, a baseline can be obtained in 1 to 3 hours. With a little bit larger, it'll take us a day. With a very large structure, it'll probably take us 2 or 3 days. But being able to look at frequency, damping in their nonlinear form, and look for any nonlinearities in the displacement, the mode shape of the structure, tells us everything that we need to know about the state of health of a structure. So how do we extend the life of a bridge? As long as we have that ability to measure the performance of a structure, then we have a route in to do this. SHRP2, which was the second strategic highway research program in 2013, said what we should do is assess service limit states more accurately. Look at the performance of structures. Look at the components and get specific guidance about elements as well. SHRP2 was an amalgam, Federal Highway Administration, the American Association for State Highway and Transport Officials, and the Transportation Research Board. What we do and what the methodology that we use actually addresses all of those things. We can measure the performance, we measure the holistic behavior, we can calibrate existing models and learn what's wrong with them, and we can synchronize a maintenance program with the performance measurement as well. So the measurement of the dynamic performance of a bridge answers all of the questions posed in SHRP2. We're running short on time. I want to go on to the examples here. Basically, what I was saying here was that if you have a maintenance program which actually addresses maintenance, spends more on maintenance as time goes by, you will avoid the big league event for which you have to pay a lot of money. So we have a number of examples here. We have the RFK complex in the US, Rail Truss Bridge, a standard bridge out on Long Island, Boston Commuter Railway Bridge, Andrews Avenue Bridge in Florida, the cables on the Manhattan Bridge, Lithgow Stone Arch Railway Bridge in Australia, and the Mosholo Stone Arch Bridge, which we used for scour effects. Now, each of these has taught us something, and I want to just quickly share some of those lessons from these structures. This is the RFK Bridge in New York City, and we did seismic and wind analysis of the RFK Bridge. That is actually 3 separate bridges, the suspension span, lift bridge, and a truss bridge. So we measured frequencies, mode shapes, and damping to calibrate a finite element model. And you can see from the blue dots, those are the positions where we made measurements on the structures. Here you can see triaxial accelerometers. Because the frequencies that we're looking at are so low, we don't have to drill into the structure or anything like that, just attach to it. And this is what we got, 0.195 as the vertical first mode. There's a listing there, and this is being recorded, so you'll be able to see the details of those. That's the suspension bridge. And this is the power spectral density taken at one place on the bridge. And you'll see there's a number of modes of vibration that clearly come through. And when we analyze those at the measurement positions, then we find that we've got the normal mode shapes. Top left here, for instance, we've got 0.195, but we have measured a place where the response is different on the two sides of the bridge. And that occurs in this mode as well, in mode 3. So we've got areas of the bridge where we think there is lower stiffness. There we've got a 0.6 hertz, mode 8, east side and the west side of the bridge twisting as well. And this is a complex mode of vibration. We also find that the approach spans interact at the frequency of resonance with the main span. So going back there, we've taken that fundamental frequency and we've looked at the damping response using something called the random decrement, which is a way of analyzing random response of a structure and getting out the nonlinear damping and frequency behavior. So we've measured there on another bridge there in this complex, the Bronx Kill Trust Bridge. There again, some measurements of the main part of it, and close to the structure, close to the roadway, where no closure is necessary. We were also able to look at the towers with the suspension cables on them to be able to look at the frequencies of those, and made measurements on the approach spans as well, looked at the frequencies there, and got out measurements of frequencies on the lift bridge. On the lift bridge, we've got damping, which again had this very low frequency response, presumably by interaction, in this case, probably with the abutments, but damping leveling off at about 1.5%, something like that. In this case, the frequency is very stable. Looks almost as though the frequency is unchanging with amplitude. And we've got a series of modes of vibration. First mode of vibration has a very high damping ratio with it as well, and presumably caused by that interaction with the abutments. And here you see an indication of the sort of thing that you can get from reverse engineering. We know what the mode of vibration is. It's translational, and damping is high, so it's losing energy. So the implication is it's probably interaction with the abutments. We're also able to look at the vertical response, in which if we get a different frequency for an equivalent footing, then what we've got is a different spring constant for the soil underneath the supports for the bridge. Coming on to another one, this is a rail truss bridge, 100 years old, and we looked at this. We looked at the modes of vibration, fundamental mode here at 1.76 hertz, the first anti-symmetrical mode, a train going over it, and the truss actually supporting the structure, and there's a real-time response. Now, top right here is a picture of the way this structure was built. And in fact, the style of it is very similar to a lot of structures that were built 100 years ago. They had a number of steel members and they were connected together. In fact, there is the first of this type of bridge is in Singapore. And you see the same sort of thing. There is a steel plug which goes through at the end of the steel member, and it's assumed that they all take load. But while we were there, we heard these chattering. Chattering, that's what this technician heard at the Tay Bridge when he went to inspect it. So what this actually implies is that some parts of the bridge are not taking the load that they're designed to take. And visual inspection, you can actually hear that that's the case. We looked at this bridge out on Long Island, and the thing that I want to show you here, because I'm running short on time, but we calibrated this for a finite element model, and we looked at the relationship of the fundamental frequency with the stress, with the strain which occurred. And we did that by passing a truck over the structure, measuring the strain underneath the structure, and finding that the natural frequency changed as per the strain of the structure. So it looked as though we've got a methodology there for saving a lot of time and effort. I'm going to move on over this one because this is another calibration effort for a structure. This is a railway bridge, and it was actually damaged, badly damaged. So we looked at the response and found that the damage was actually progressing. So we looked at this sort of thing as trains were going over, and we took the analysis, used it to excuse me, to calibrate the model, and found that actually the best calibration was obtained if we found that only part of the structure was interacting with its foundation as it should do. The rest of it was moving around. So in the end, we actually got measurement and model a reasonable accommodation between the calibrated model and what we'd measured. Andrews Avenue Bridge in Florida, we'd looked at this because there was piling going on nearby. In this particular case, we measured the response. We got the first mode of vibration, and there again, you can see using damping, using the random decrement, we got damping, and we got the natural frequency. Damping is quite high for that. There's car traffic moving past, and there is the tilt of the structure because of daily thermal changes. And there's a day when piling had occurred and the pile driving was very close to the abutment. We were looking at peak particle velocity. All we do is just take the simple harmonic motion version of the acceleration. And there, in the response, you can actually see that the piling occurred at about 33 hertz, structural resonance of 4.5 hertz, and you can see the two signals beating with each other. And there we have peak particle velocity 50% larger at one end of the structure as a result. I'm going to move over with this and try to just come to a halt here. This is a building in Australia, a structure in Australia, three arches, and it's stone built. It's 100 years old as well. It's in Lithgow, which is actually only about 15 miles from my son's home. So in this particular case, what we were looking for was the response of the structure. And my computer is frozen up again. Bear with me for just a moment. In this particular case, there was a problem. There were cracks inside the structure, and they were very worried about it. It had been restored, it just held together, as it were. And in this particular case, what we'd got was a speed restriction on the structure. And for that purpose, we were looking to see if we could calibrate a finite element model. Well, we did that. And at that stage, and if my computer will let me, then I will, I'll show you some of the results of that. Here we go. So we have vertical modes of vibration, all of them 14 hertz, 15 hertz, 17 hertz, and they involve motion of those three spans. Now, in each case, the frequency from the random decrement comes out consistent with what we got. The damping comes out quite high, 5% for that fundamental mode, 11%, 12%, dropping down at high amplitude down to 8%. So what we've got here is modes of vibration. There's the first one, in which there is antisymmetric behavior. There's a second, in which we've got torsion. Complex modes, indeed. And then a number of modes of vibration which involved only one of the spans. So there's the model, there's the structure. And the question was, can we release the train speed restriction? Well, this bridge is actually very close to Sydney, but the Indian Pacific goes over it. The Indian Pacific goes all the way across to Perth. The round trip is 4,000 miles. So it's quite important to Australians. So we looked at the response, and there's a response of a heavy train going on. Did the calculation for this complex response to look at what we could do. What we found was that those struts holding the bridge together were actually quite acceptable. They were doing a good job. And in fact, the bridge was holding itself together under arch action, and the arch action was very efficient. So the answer was yes, certainly. We can raise it, not very far, but we can. Instead of 40 kilometers per hour, they raised it to, I think it was 70. Moshulu, we looked at that, and the idea here was to see if we could distinguish scour by looking at the ratio of modes, one frequency to another. So with scour and without, we looked at that, and we found that with scour, we got a sufficient difference in the frequency that we could actually use a simple measurement of frequency to be able to identify whether scour was occurring. So the assessment of the useful life of a bridge. Wind tunnel tests are good, but they're incomplete because you have to guess at the damping value for structural damping before you do the analysis. You can put in radiation damping through soil structure interaction and have a good guess at that, but it's difficult to do it for the structure itself. It has to be estimated, at least if you're relying on a wind tunnel test. So damping is complex. It's got structural and aerodynamic, but from this random decrement analysis, we can actually get the aerodynamic instabilities as well. So we get the whole body response. I'm going to press on over that, but this one, a colleague in Japan said, this is the information we've got. We got this 3-part curve, low amplitude plateau, a rise. Most damping measurements are made in this area. We then have wind resistant design in this area. We have strength design. We have occupant comfort limits. But there are some things, including Ron Mays' test, that suggest that damping may actually decrease at high amplitude as well. Now that would be a problem for seismic engineers if that's what we get. So the problem as well is compounded because damping in its 3-part curve will actually start low and rise to a higher value. If damping is low at low amplitude, it will race through to the higher amplitudes much faster, and it will spend more time. The structure will spend more time at the high amplitudes. And that explains a comment that we were faced with in New Zealand when we were testing some buildings there, in which the city council asked us, we've designed to the code and yet we're getting damage. Why? Non-linear damping. That would appear to be the answer. So the benefits from using this type of technology that we use We have rapid measurements. We can do continuous surveillance. We can send those signals over the internet for you to look at inside your office. Automatically available of data from sites. We can have alarms and warnings if necessary. And if necessary, if something unusual happens, we're on the phone immediately. And people do phone us up and say, something's just happened. Can you help us? So quite often we can look at our baseline, look at our immediate response to the structure and say, you're okay, you dodged a bullet. So in conclusion, the technical developments have made these techniques very powerful, and they're coming. There are performance measurements coming into codes of practice. How do I know? Because I'm on a committee which the ASCE has formed to look at the implementation of performance criteria directly into codes of practice. So we can look at the ongoing assessment of construction activity. We can allow the calibration of finite element models. We can allow safe redevelopment because we look before and after. It gives peace of mind as well. So to come full circle, we come to the high-rise bridge in West Seattle at the moment, in which there is intelligent monitoring. Well, maybe it's intelligent, but it would be probably a little bit more information coming back at people if there was a holistic approach to looking at the information which is being generated. And this is in Brazil. We have been invited to do a test on other bridges in Sao Paulo as a result of that collapse that they had using our technology. So, ladies and gentlemen, thank you very much. Please be aware of the potential surprises of the natural world. And if you think that you might like to collaborate with us and to try to solve problems that you've got, then please, we would be very interested in doing that. Thank you very much.
Thank you, Dr. Jeary. There are a couple of questions in the chat room. If you'd like, I can read those, or you can read them yourself. Would you like me to read those?
Yes, if you could, please, that would be a good idea.
Sure, I'm happy to. What kind of damage will happen in the bridge when the bridge faces scoring problems underneath the pier?
What will happen in the bridge? Well, one of the things that you need to check for is the elastomeric bearings as well. That's one of the things that people are particularly concerned about.
Whether I think they intended on saying scour, Alan.
Oh, I beg your pardon. I didn't hear you properly then, Gerald. What happens with scour? Well, if you have scour occurring around the foundations of a structure, then your assumptions for the way that a structure is going to be supported have gone out of the window. So if scour gets bad enough, then you don't have the lateral stability. You may not even have the vertical stability. So that can happen. But one of the things that, one of the telltales is that you get a change to the damping value when scour occurs. And thank you, Tom, for alerting to that. Tom is my colleague from STRAM.
Okay, thank you. A couple more questions. If a bridge is built using self-healing materials or energy-absorbing material in critical components, would that notably change the overall holistic damping behavior of the bridge? Would this make the structural health monitoring more difficult?
The straight answer is I don't know, but there's a longer answer that I can give you. First of all, I would expect that there would be a gradual change, but if you are looking at the holistic behavior of the structure, then that doesn't matter. because if it's self-healing, then what it's going to do is one of two things. If it's going to dissipate energy, then that will show up in the damping characteristic. If by self-healing, you mean sort of welding bits of the structure together, if it behaves like that, then you would expect damping to reduce. Either way around, you'll see a change in damping, and you can put on your Sherlock Holmes hat afterwards and have an analysis of what has been going on. But the last thing that I'd like to say in that is all of the things that we try in structural engineering give us surprises in one way or another. Because what happens is we add plasticizer, we add chemicals which will allow concrete to set faster. We use super strength steel, things like that. We use glass as a structural material. And we don't actually know until 10 or 20 years down the road exactly how they behave. Because looking at things which are occurring is one of the important things that we do in structural engineering. You know, one of the biggest disasters that's ever occurred in structural engineering, it killed 20,000 people. It happened in the year 327 BCE, and it was an arena, a Roman arena, which collapsed and killed 20,000 people. So throughout history, as structural engineers, we've learned from our mistakes.
Okay, thank you. A couple more questions. How do you see pattern recognition, artificial intelligence, or machine learning as useful or not so useful in mining the monitored damping data?
I think artificial intelligence is a great idea, and I think that there's a good future for it. I would also say, though, that it needs calibrating. Artificial intelligence can give you a short route through to having a look at how something is behaving and looking at what's happening to it. In the same way that finite element models need calibrating, then artificial intelligence will do as well. But the future for it, once we've got the wrinkles ironed out, I think is terrific. So if somebody's doing that and they want to work with us to have a look at something that's going on, we'll gladly work with you.
Okay, 3 more questions. How do we know damping describes the structure after severe yielding and or buckling?
Damping is a modal parameter. So what it does is to give you information about a single mode of vibration. So it's associated with that mode of vibration. Now, if you want to know about the structure in more detail, you may see an excursion of the damping parameter in a single mode of vibration. The next thing to do is to look at as many other modes of vibration as you can, because there is something called modal ratios. And if you have enough modes of vibration, you have just one more mode of vibration, then there are imperfections in the structure, and then you put together all this information into those, reverse engineer the influence functions of all those modes of vibration. You can identify where the problem occurs. So you look at frequencies, displacements, and damping together and look at the information that they're telling you together. And quite often when you do, you can actually come to an identification of precisely where the problem is in a structure. You can't necessarily do it straight off. If you see a damping anomaly and you've only got one mode of vibration, you can go back through fracture mechanics and say, okay, well, we've got an imperfection which is 3 feet long or something like that, but you won't know where it is. That's the only thing. So the more information that you get, the more you can actually identify where the problem is occurring.
Okay, the next question. I saw some high response in damping, such as 7.5%. With that level of damping, would there be risk that the damping measurement may actually induce microcracks in the concrete bridge?
It's probably more of an indication that microcracking is occurring. As a matter of fact, in Hong Kong, we took a structure which had been affected by a typhoon, and we took concrete samples out of various different levels of the structure, and we then looked at those under a scanning electron microscope, because of course the fracture mechanics model tells us that there will be changes in the structure. As energy is dissipated, then cracks elongate. But it gets worse than that, because as you get smaller and smaller, you get into the atomic structure of the material. And we did that with scanning electron microscopes and found that where the concrete samples had undergone different stress histories, we had, from the same original pores of concrete, a different chemical composition. So in other words, the energy which was being dissipated was no longer elongating the cracks, but was making chemical changes within the matrix of the concrete.
Can you comment on any recent advances in non-destructive testing methods that have helped improve structural assessment?
Yes, it's a mixture of advances, actually. First of all, electronics, because if we get the electronic noise so low that we can measure more precisely, that's very helpful. So our SKG and those accelerometers, excuse me, have come out of military technology, which we've adapted, and we've put that together so that we can measure at very low amplitude. That's the first thing. The second thing is the random decrement and the nonlinear analysis of structures. That's only really happened in the last 10 years, where we've been able to do that really well. Actually, I had something in my PhD thesis in the 1980s, but that was a forerunner. And then 5 years ago, we were able, with all this added precision, to be able to look at the risk ratio. So that's a very big thing, which is now possible. And doing it all over the world has become possible. But I'll tell you what the next big thing is going to be as well. Right now, we take these high precision accelerometers and we walk with them to a position where we want to make a measurement. We connect a cable to our SKG. Two things that we want. First of all, we want drones to be able to place them in the position that we want. And the second thing is that we want Wi-Fi to be able to connect to our data center. And right at the moment, we're making measurements 300 times a second with what we do. Right at the moment, there isn't enough bandwidth. So we want more electronic capability to come up. That's where we're going within the next few years, I would say.
Okay, thank you. One last question. Would the patterns be similar if shape memory alloy / engineered cementitious composite, I hope I said that correct, were to be utilized at the most critical joints?
Once again, my straight answer has to be, I don't know. The longer answer, though, is that I would suggest, I would expect that with shape memory, you are actually depositing energy into the material, under which circumstance it ought to take energy out of the structure to be able to do that. If it was taking energy out, then we would see an effect in the damping ratio, but we'd only see it after it's gone back to its original shape. It's an interesting concept, an interesting problem to look at. I'd be very interested to be able to see some data so we could have a look to see if my my estimate of what might happen would actually occur.
That's all the questions that I see in our chat room. So I did mention earlier that if you have more questions, you can email Dr. Jeary. Thank you, everyone, for joining us today. Thank you, Dr. Jeary, for the time you've given us that we can't give back. We really appreciate it. It was very interesting and very engaging. So thank you, everyone, and stay in touch with us and be looking for our webinar for next month. Have a great day.
Thank you very much indeed, and thank you very much for participation, for everybody. And as Cheryl says, if you do want either more information or just to get in touch, I'll be very pleased to liaise with you. Thank you.
Thank you, Dr. Jeary.
Thank you.
Thank you, Dr. Jeary. This is Xiaoming. It was really nice talk. Sorry, the hiccups with the internet.
Oh, that's not a problem, Xiaoming, and thank you very much for inviting me. Yeah, I'm not sure whether it was the internet or whether it was something on my computer that was causing a problem.
One possibility is maybe your file is so large, you have so much information, just never know.
That happens, and as a matter of fact, at the last minute, I had opened some other PowerPoints, and when I do that, I do sometimes get problems. So my apologies for the problems with it.
I think by having the slides and the YouTube thing, the video online, it will definitely reach more people. Because I know a lot of folks, affiliated with the center, they probably cannot come at this moment, but they will get, access to it. And yeah, it's highly relevant. And I think the Q&A was really engaging, yeah.
They were some very interesting questions.
So, well, where are you right now?
Oh, I'm in Harrison, New Jersey. Yeah, I'm not on the beach.
Yeah, I'm not in California either. So, all right. Yeah. Well, just take care.
Yep.
I think things have improved over there, right? Like the COVID-19 situation. Well,
they say it's improved, but quite honestly, I'm in isolation here, and we operate with mobile offices. My colleagues have been out to 3 sites, while this has all been going on, but nevertheless, there's a lot of people who are behaving in a very strange way. And
that's the trouble with this nation. At least 20% of the population don't even care.
Absolutely. I think that they must think that they're bulletproof, and I'm supposed to be somebody who's more at risk, so I'm quite keen that they do follow the rules.
Yeah, it's just so much uncertainty, kind of like when you look at your structure. Yeah, there's so much uncertainty ahead of us. We don't know what's going to happen in the winter. Yeah,
that's right. Now, listen, we talked about collaborating before, and that's still, as far as we're concerned, anyway, a very good idea. If you've got some things that you would be interested in doing.
Sure. Now that I know a little more about your approach and things, maybe for instance, we could develop some sort of one-page problem statement for DOTs. Like my local DOT, Washington State DOT. And again, I was the one asking about the artificial intelligence question because I see the elegance of keeping it simple. Like a risk ratio and all that, but then if you have a ton of data over the years, maybe there's some more to it we can dig out potentially. Anyways,
absolutely, yeah. And it came as a surprise to people as well when we originally came up with you have to calibrate finite element models, because if not, and then we showed them particular models saying they're 50% off. 50% is just far too much. But, it's a question of what you include into your model. If you say, oh, that's non-structural, so we won't include it there. Does the panel that you're talking about know it's supposed to be non-structural? And I'm sure that the same sort of things will go on in AI. But if it's calibrated, it's incredibly powerful.
Yeah, and also you look at the fact you were talking about 115% and all that, because traditionally people always think a safety factor of 2 or 3. They were thinking, okay, average is pretty much bulletproof, but it's not.
Yep. That's right.
Yeah, I think there are ways. I just need to think about more, but there are ways probably to approach SHRP, and but sometimes if a state DOT like Washington is willing to lead the transportation pull form mechanism to get more states involved, because this is more than a local problem. It's actually many of these DOTs share the same concerns. I think
sure.
This again, I'm not a structural engineer by training, so that's not my, So, but I could bring in, structural engineers. Actually, some of them were, from our center were in your talk. So yeah, even though we got a relatively small audience, but people are really, engaged. So.
Okay, and certainly that idea of a one-pager for a DOT would be very interesting. I'd love to work with you on that sort of thing.
Yeah, I don't know whether or not I mentioned this to you. We have a new journal with Springer Nature, and we're trying to publish some sort of commentary type of articles, so that, with your decades of experience, you might be the, because I saw a recent manuscript, for instance, talking about new directions of dealing with rebar corrosion in reinforced concrete. I haven't seen the manuscript, things like that, like 5,000 words with probably no more than 30 references, but just more, almost like a pinning piece, like where the future should.
You did mention that to me before, and I've started writing it, but we have been so busy that each time I get to a decent stage in it, I've been called away to do this or that. And
that's fine.
Funnily enough, even with the pandemic, we've been absolutely weighed down with stuff that we're doing. And quite honestly, a lot of the information comes back, and you say, yes, well, we do it in a very short time. We've got the information, but we agonize over some things. Between us, we look at something which is unusual, and we have a discussion for a couple of hours about what's actually going on and what the importance of it is. And
you're basically the bridge doctor trying to diagnose. And
exactly, yes. Yep, sure.
Okay, cool. I'll be in touch. Once I'm above water, I guess I'm on deadlines too. So.
Okay.
Thank you so much for the talk.
Very good. Well, thank you for giving me the opportunity. Much appreciated.
All right. You take care.
You too. Stay safe.